correction of conductivity, which is very convenient right here, delta sigma equals integral over two-dimensional momentum q over 2 pi squared times hxx, which is just a number, so we can put it out of the integral, times Cooperon of omega equal to 0 and of q. It is this loop diagram, this loop, has momentum q going around it. And we have to integrate all this. This is the last momentum which is not yet integrated. And this is h. So if I put everything together, this thing equals, yeah, let's do that. So this is h minus 2e squared mu d tau squared. Then integral, two-dimensional integral of q is q dq divided by 2 pi. And then Cooperon has 2 pi mu tau squared, which is q independent, and here we have 1 over d q squared minus a omega, but omega is 0. So this is the full expression, and you see right many terms that cancel out. And the result is the following. So e squared survives, minus survives, d survives. Well, actually d cancels this d, and this 2 pi goes there. So what is left is minus e squared over 2 pi squared integral dq over q. Is it correct? And this integral is what?
Infinity.
Infinity, right? So the quantum correction, although it's a small correction, actually diverges. This is important property. That's why we need to take it into account. And well, once again, I said it is small because look, sigma 0 is much larger than the square of h. And delta sigma is, sorry, I always forget h. So
we use the assumption here that the momentum is small.
Yes, we use the assumption that momentum is small, and
So the upper cutoff
q L is much smaller than 1, so the upper cutoff value is L inverse, but it diverges also at small q, and at small q this is a very accurate expression. Now somebody tell me how to make it finite.
Phasing time.
No.
System size.
Stay silent.
System size.
System size, exactly. This loop, with this momentum q, as was suggested previously, can be also understood in real space. The smaller is the momentum q, the larger is this loop in real space. So, since we actually consider a system of finite size, we can say that, for example, that q is quantized, like in the box. It's quantized to values n over h, very, very dense set of values. So this integral of q is actually a summation of many, many, many dense values, but there is a smallest one, which is not 0. The smallest one is a inverse the size of the system.
Why don't we want to cut it with the phasing time?
Because I don't know what the phasing time is.
Inelastic scattering. So
Because I don't have inelastic scattering. Temperature is 0. No inelastic scattering. So the answer is minus e squared over 2 pi squared h, the logarithm of a divided, the system size divided by the mean free path. So this is a quantum correction. Sigma 0 is large compared to e squared over h. This correction is of the order of e squared over h. It's much smaller, but it also contains a large logarithmic factor. So each individual diagram here in this letter is of the order of e squared over h. But when you sum the letter, sum the series with 1 line, 2, 3, 4, 5, 6, the sum logarithmically diverges. It's like 1 over n. If you compute individual diagrams, you can see that they scale like 1 over number of dash lines. Very good. So, and also important thing, it's a minus sign here, it's a negative correction. So, quantum effects provide a small correction to the classical conductivity, which is on one hand negative, and on the other hand not so small as we expected originally. And it also depends on A. The original conductivity, sigma 0, does not depend. This one depends on A, and this is exactly what we wanted for this plot that I just erased here, that in classical limit beta is 0, conductivity does not depend on A. Now we have a correction which does depend on A, so its beta function deviates from 0. And beta function, just a reminder, is d log g by d log A. So this is not A. And g is the same as sigma. And this derivative is what is it? It's 1 over g times dg by d. Okay? And this is the truth of logarithm. And g is the same as sigma, so this derivative, since sigma 0 does not depend on a, we can differentiate just this terms in a logarithmic way. It's minus e squared over 2 pi squared h, so it's minus e squared over 2 pi squared h g. And now I remind you that g actually was measured in units of e squared over h, which is, so this should be g. So I should cancel out e squared.
E squared and 2 pi.
H and 2 pi. So it's just pi. It's 1 over h. Well, it depends. You can take your units e squared over h with bar, without bar. Some people include this pi also there, so this is just like 1 over g. Doesn't matter. It's just the definition how you define what dimensionless conductance is. But this plot here, which was erased, I just recreated. It was like this for 2 dimensions. This is log g here. And this negative correction tells us that when we go from the side of large g, we deviate downwards. The function has a negative correction. So this is a proof of 2 things. First, the scaling hypothesis is correct up to these terms. So it was correct in the fully metallic limit, but it was just 0, Ohm's law. Now we see that quantum correction does not break this hypothesis, it just tells us how this beta function should be modified. And the second thing it proves that in this model, 2-dimensional methods indeed do not exist. The quantum corrections destroy metallic behavior and eventually will bring the system to a fully developed insulator state as we increase the size. We increase the size, this correction is negative. It's a small prefactor here, but logarithm grows, so at some point, this correction will overcome the original value of sigma 0, and we will end up in an insulator limit.
Just a small technical question, why we actually neglected the dependence of hxx on q?
Because it will not lead to logarithmic. So it will add some power of q in the numerator, and it will not be logarithmic conversion, it's just some finite.
constant and the logarithm.
Constant, logarithm.
Oh, okay.
I also have a technical question, so how much time? Because I see the clock there, but I do not distinguish the two levels.
25 more minutes.
5 more minutes.
25.
25. Oh.
35.
35.
35. Yeah, 12, 15, 35. Right?
Very nice. So let us now discuss the following generalization of this calculation, namely what happens if we recall that electrons in metals actually have spin. This was all for spinless electrons, just some scalar particles, the function is a number, everything is a number. So the spin is working. Spin tells us the following thing. First of all, everything should be multiplied by 2. Sigma 0, the conductivity of a metal, is now not E squared mu E, but 2 E squared mu. This is spin. What about correction, delta sigma? What about? Anton, what about the correction?
Thinking whether it's so as trivial as it looks.
Exactly. It's just twice larger, it's minus 2 E squared over 2 pi squared h and the logarithm. Well, if we have spin, but the Hamiltonian does not depend on spin, so spin is always degenerate, better momentum, and also scattering on impurities is spin independent, spin up and spin down scatter exactly the same way. We have just conductivity due to spin up, plus exactly the same one due to spin down, and the correction due to spin up, plus the same correction due to spin down states. Now, if I ask how this correction can be understood in terms of this diagram, it's very easy. We have a ladder, which was called Coupon, a ladder, and now each line, I mean the upper line and the lower line, they carry some spin. So it can be green function for spin up or for spin down. And the second one can be a green function for spin up or for spin down. So for the Couperon, there are actually 4 possibilities how we can put spin labels. And these 4 possibilities, we will give names to them. Possibility number 1, spin up, both lines carry spin up, plus spin down, divided by the square root of 2. This is just normalization. Now, very tricky question. What's the name for this state? Louder? This is singlet. This is called singlet state, which is quite counterintuitive. And then there are the other combinations: up, down, down, up, and the difference here: up, minus down, and the square root of 2. And these 3 things are called 3 components of triplet state. So I'm sure now you are tricked completely. Actually, the reason for this strange notation is because it's coupon. If you apply if you reverse the line below, it also reverses the spin transition. Then singlet becomes, the diffuse on the singlet becomes the usual singlet. Becomes usual. So there are 4 possibilities, and each of them, they are all identical. Each of them give 1 over dq squared minus omega, because nothing actually depends on spin. Now look, we have 2 spins. We should have our correction with a factor 2, but we have 4 Cooperon modes of the system. Each mode has a pole here. Each one can provide a logarithmic correction. And we have 1 singlet and 3 triplets. How do we make 2 out of 1 and 3?
Subtract.
Yeah, exactly. So this delta sigma, sorry, the one that I have here, I will write it in the following way. It's e squared over 2 pi squared h 1 minus 3. That's minus 2. And then I will say that this one is due to singlet mode, and these 3 are due to triplet modes. And actually what I'm now telling you is not anything rigorous, it's just hand waving. Yeah?
Why the answer for triplet is not 0? Because for me it looks like that ring functions are diagonal in spin space usually, and then for different space projections the diagram could be 0, and the same for different between up, down, down.
Just take this component of triplets, up, down. We have up spin on the upper ring function and down spin on the down ring function. And then you have a scattering on impurity which is spin independent. So this spin up remains to be spin up, the spin down remains to be spin down. And then it continues along the whole ladder, so this whole ladder is proportional to up-down in spin space and to this thing in real space as it was for spinless system. Or maybe I didn't understand it.
So the spin structures
Spin structure is just
will keep
decoupled completely, because scattering is spin independent.
it's separated from the
Yeah. So actually, I did not prove this result. I just tried to write it here because I know that there are 4 modes, and I know that the total result should be -2, and I know that all triplet modes are equivalent because we can rotate in spin space. So each of them should give the same result. That's why I put it right here. But there is also a rigorous derivation of this, which I just don't want to do. Yeah.
Why can there be a difference at all between these?
The difference is actually due to
H.
the mechanicals.
You never
So
said
the
that.
mechanicals also has spins.
You didn't introduce the word I mean.
Oh, sorry. I introduced the letter H. Mechanicals. And it is you can also, so if you have, for example, single state, you have spin up, going here, and spin up here and from there. But you should also add spin down. And, well, as I said, I don't want to derive it. So the difference by this minus sign is due to this box of time. So if you compute it with spins accurately, hopefully it will reproduce. Yeah. If no other questions, then there is another explanation why do we have these 4 components, 4 spin components of the Cooperon, and all of them have singularity at small q and omega. I told you in the very first lecture that this singularity at small q and omega, this pole, is related to the conservation of the number of particles. Now when we have spin, and spin does not participate in anything, it's always conserved, we have two conservation laws. We have conservation of spin-up density and independently the conservation of spin-down density. That's why we have more than one propagator that has a divergence in small q. Well, actually, we have 4 of them, but there are only 2 conservations. But on the other hand, we have like 2 singlet and triplet, and with this. Oh, okay, this actually means that. So I'm just saying that we have more than one propagator, more than one singular propagator, because we have more than one conservation. And now imagine that I take the same system and I add spin-orbit coupling. Spin-orbit coupling. Spin-orbit coupling means that I should complicate my green functions. This psi phi will now depend on the spin as well. So the energy depends on momentum and spin. And the green function becomes a matrix in spin space. And now the spin is not anymore conserved along any of these lines. And there is no such simple expression in Cooperon. And that's why we will not compute this. But what we can say is that spin-orbit coupling breaks the spin symmetry. Spin can flip when it's propagated or when it's scattered in impurities. And that's why there is no 2 separate conservation laws. Now there is no separate conservation of spin-up or spin-down. There is only conservation of the total density. And conservation of total density means that this singlet Cooperon, the singlet channel, it is still of the same form, but all triplet states actually require some mass. There is plus some constant in the denominator. In real space, they start decaying. There is no diffusion of spin. Spin does not diffuse because it decays, it's not conserved. So with spin-orbit coupling, these triplet modes cease to exist. Well, they still exist, but they are no longer singular. And this singularity was needed to get a logarithm. We had this 1 over q in the integral, so only we need that at small q this function really diverges. Otherwise, the correction will not be logarithmic.
We do not have a sign of the denominator.
And yeah, and since we killed the triplet, it means we kill this -3 contribution, and we are left with +1.
Then there is methodology transition.
So for spin-orbit coupling, delta sigma is actually positive, plus, and is actually twice smaller. It doesn't have this 2 here. It's plus e squared over 2 pi squared h logarithm with, well, there is no 2 here, but there is 2 in sigma 3. That's it. Nothing more to do here. And as you correctly mentioned, it means a transition in 2 dimensions. So I draw, actually I have this picture. So we have positive correction to conductivity, which means that beta function deviates from 0 in the positive direction when we come from classical limit from the scale. We draw this scale with negative direction. This one deviates to positive directions, but eventually, as we add more and more and more disorder, conductivity becomes smaller and smaller. Eventually, we should anyway go to the insulated state. It's 2-dimensional picture, and there is a point called 0. Now, this situation is called, has a name. This line below was a very standard model where spin was a conserved quantity. Spin conserved. Just this one below. And this situation is for some reason called orthogonal. And there is another situation when spin symmetry is violated. due to spin orbit coupling, spin violated. This situation, for some reason, is called symplectic. Let me finish. And actually, there is a third situation when time reversal symmetry is broken and when there are no couplings at all, no singlet, no triplet. It happens, for example, when this psi of p, as I discussed, is not equal to psi of minus p. When we reverse the arrow, it's not the same as the default number. And this third situation actually has this delta sigma equal to 0. But if you compute the next order correction, which is for some more complicated diagram, you will find that the correction is non-zero. It's even yet much smaller, but it is still negative. So there is a third situation which is in between these two, which also approaches zero from below, but comes closer to zero. So the correction is smaller, and this third situation is when time reversal symmetry is broken. Time reversal is violated, and it has a strange name, unitary. So there are these three words, orthogonal, unitary, symplectic for these three cases. And this word tells you which actually beta function you have. There are three variants of this beta function in a two-dimensional system, depending on whether time reversal or spin symmetry is preserved or violated. Actually, in this unitary case, you still can either have spin symmetry or not, but this result does not depend on it. So it's the same both for conserved spin or for non-conserved spin.
So it doesn't depend on the type of spin orbit like Raj, but there is still with the same.
Yes, it is the same. There is also a model which is called spin orbit scattered when the Hamiltonian is conserved spin, but scattering and impurities depends on spin. The only thing that is required is in these both cases that the time reversal symmetry is preserved. So spin orbit should not violate time reversals. Are there any other questions? Yeah.
When I consider this plus 1 and minus, plus consider minus 4 triplet, should I consider current operator for conserved speed? Because it seems that if current operator is conserved speed, how can I use retarded function for one speed and advanced function for other speed?
This is a very good question. This is exactly the reason why I didn't want to discuss it. Because you're right. It's not as simple as I tried to present. Well, actually, when the spin is conserved, you don't need these triplets and singlets. You can say that you have this diagram for spin up everywhere plus the same diagram for spin down everywhere, and you get -2. And if the spin is not conserved, you are not even allowed to say if the spin is up or down here. It's not complicated. Because spin might not have any particular value, even on a single green function. So you should use not the plane wave states, but rather some states that depend both on momentum and spin. And the eigenstate with a given momentum can have, so let's say, quantization axis and spin space may depend on momentum. To diagonalize it. So it's very complicated, but so I just took this shortcut because I know what the correct result is, and I know that I can reproduce it this way. Yeah.
If we don't have time reversal, then what kind of diagrams contribute? Like, so this diagram is 0, right?
Couperons are 0, only diffusons exist. We will compute actually these diagrams in the lecture, this +2, +3. But since you asked, the diagrams that is one of them are made. Sorry, these are attachments. It's one of them that there are more. So it's like two diffusons which are cross. Do I don't have it.
15 minutes.
Wow,
Yeah.
great. It was 25. Like,
No, I told you, you have 40 minutes.
I had 40. Not, okay. Very, so, so this is our main picture. We should remember it because it will reappear many times in future lectures. And right now I will present some other calculation of the quantum correction, alternative calculation, which actually gives the same result in the end, but which is much more complicated. And the topic is this. It was quantum correction to conductivity. Now, the new topic is quantum correction to diffusion. So we know that electrons diffuse in metal. There is a diffusion equation, and actually, on a classical level, this diffusion is equivalent to conductivity. There is Einstein's relation that relates conductivity to diffusion constant. So if we have quantum correction to conductivity, we should also have some quantum corrections to diffusion equation. Yes?
Could you go on comment on whether we could also find beta functions in 1D and 3D?
Actually we even didn't find it in 2D. We only found a small correction to classical limits. We still did not derive this part. And the same can be done in other dimensions. So we can compute corrections to this constant in any dimension, but it becomes harder when it goes closer to the insulated. So these corrections. So for example, in 1D, we have in 1D, we more or less can derive the whole function. But in 2D, to derive how it goes here, you need to add more and more corrections, and it's not that easy.
It's difficult to generalize previous calculations for the case when sigma depends also on non-zero Q and non-zero omega.
Sigma depends on what?
Non-zero momentum and energy.
No, it's very easy. It just replaces it, so this scale 10, which cuts the logarithm, can be replaced by frequency, or it's an infrared cutoff for this thing. So if you have conductivity at finite frequency, you can plus the omega here. Now your logarithm does not diverge at small q, it's cut by u, so it's logarithm of square omega tau.
And if there is momentum,
Square root means 1/2. Sorry?
if not energy, but non-zero momentum.
Conductivity at finite momentum, which is exactly the same as the finite size of the system. I mean, it's momentum, it's in momentum space, and finite size is in real space, but actually it's the same, if you like, the same object. So if you have finite momentum q, you just replace it by 1 over q. And if you have finite phasing, you can also add it here in the denominator. Yeah, okay, so quantum correction to diffusion. We have a diffusion equation, we have it somewhere. And diffusion equation had a propagator called diffuser, which I already had once here. And this propagator was this kind of a ladder, with now arrows pointing in opposite directions, without once. And it was 2 pi nu tau squared d u squared minus n. This brackets. Now, I want to add quantum correction to this object. Quantum correction means insert diagrams, add diagrams with cross impurity lines. So I will have I will now define the following object, which I call gamma. And the following object, which I call gamma, is 2 lines, is one retarded by advanced, opposite direction, and this same fan-shaped diagram in green. And please pay attention, the diffusion doesn't have any external lines. This is how I define it here. It starts with the impurity line and it ends with the impurity line. And gamma actually starts with the green function. There are these external lines here, so impurities external lines. And as I already explained, I can distort my diagram somehow, and I will distort these diagrams to diagram like this. So this is the target line here, and the same as we did for conductivity. Advanced line here, advanced line here, target line on sorry, arrow up. Target line here, and then remove this. The fan shape becomes better. That's it. This is just the same diagram as this, and these 4 lines is what I just told you. That we have 4 lines from here to here at the beginning, and then inside we have a letter that is a tuperon that starts and ends with the impurity line. This object, gamma, wait. Just imagine that we know what this object is, we already computed it. How can we make a correction to the diffusion? We do it like this. We say that we have now a new diffusion. This was 0 diffusion, classical diffusion. And the new diffusion, which includes the correction, will be like this. It's a ladder. Then we insert gamma here, this thing, and then the ladder continues. Plus, the same thing where we insert gamma twice. And so on, plus 3 times.
Maybe there's the Bayer value.
Yeah, there is also Bayer value. I was too lazy to. Sorry. There's also the one without any gamma. And if we sum up this ladder, we get, it's just the geometric series. We have obtained 2 pi nu tau squared dq squared minus dq squared minus omega minus gamma. It's just added in the denominator with a minus sign. And I also forgot to tell you, this gamma can in principle depend on Q. So as long as we compute this gamma, we will see what changes with the diffusion. Yeah.
Why we insert in this diagram some crossing between impurity lines but still using green functions without including crossing of impurity lines?
It's because we are very smart and we know that contribution is 0. But actually, I already promised to explain it in some later lectures. Okay, so what this gamma is? Gamma is equal to have an object here with 4 green functions inside, and we have momentum q which enters from the left and goes out to the right. It's not 0 for conductivity. There was no external momentum. Now there is external momentum, which is this momentum. And we also have some momentum, capital Q, I will call capital Q, which goes along the overall ladder, and also have frequency. So this is gamma equals an integral over 2-dimensional integral of this momentum capital Q. And And then we have two objects in the integral. One object I will call h, which depends on small q, capital Q, omega. And the second object is called the fuperon, and it depends on capital Q and omega. So fuperon is just this letter, and h is this box called ring functions. It's the same h we had for conductivity, but there we had 0 q, and instead we had current vortices. Now we do not have current vortices, but we have external momentum. And this thing, actually, this thing is called Hikami box, not that one. They are very similar. Okay, so fuperon we already know. What we do not know what this Hikami box is.
What is the name of it?
Sure. It's named after Japanese theorist Satoshi Hikami. Actually, it's quite active. No, it's his invention from 1980, from the year 1980. Yeah, 5 minutes. Not enough. Well, I have a proposition. Since we have only 5 minutes, I will not be able to finish this calculation. That's why I will give you a homework. You personally. Homework is to compute this object h. But I will give you some.
A question: why we just draw 4 green functions and do not connect them with?
No, this is exactly the homework I'm going to give you. So the kind of box, this 4 green function actually is a combination of several diagrams, one of which is just 4 green functions, and the other one is these 4 green functions with one impurity line that's not this, and yet another one is the same with impurity line vertical like this. So actually I didn't draw it there, but it turns out that if you insert one extra impurity line in this direction, it will not introduce a new crossing of dashed lines. So to find the Hikami box, we need all 3 these diagrams, and let's call this H0, this we will call H1, and we write the expression H0 equals integral over momentum dvp by 2I over d. And I will now write explicitly all the green functions. So we have the arrows that go this way. We have momentum q coming from here. We have momentum capital Q going from down to up. And we have also frequency, which goes along the retardant line. So this is retardant ones. The retarded function gr of epsilon plus omega, it's this function. And p plus q. Advanced function, the next one. Advanced function of epsilon. And a minus p plus capital Q. Actually, no, this is minus p plus capital Q and minus 1. So momentum Q I draw here, omega goes this way, then I have retarded function of epsilon plus omega minus p plus capital Q, and And finally, it's times advanced function of this one, epsilon and e. That's all. Now let's check that I did it correct. Omega goes only in the retarded functions. Omega comes from here, with the retarded function, going to the Cooperon, and reappears from below in the retarded function. So omega is added only to retarded functions. These two functions, retarded advanced here, which have the arrow in the opposite direction, have minus p, while the two others have plus p. So p is the momentum that circulates here inside the box. And finally, small and capital Q. Small q enters from here, goes along this retarded line, that's why it's embedded, and then goes into Cooperon, reappears from below, and exits along this advanced line, so probably it's plus. And capital Q, which is inside the Cooperon, it goes along this pair of lines, second and third, and it's always plus here. And this is H0. Yeah, it's a simple calculation. So you write all these green functions, you expand the small q in the denominator, then you integrate the psi, you just take the residue, it's very simple, and then the result should be averaged over the directions of Fermi velocity. It's very similar to how we computed B for the first diffusion, and the result should be a number, a constant, plus some other number times omega power, and plus some third number times dq squared. Oh, sorry, we have two momenta. So it would be dq small squared plus some other number d capital squared. So you just need to extract these numbers. And then do all the same, put this diagram, just to make your life easier. These two are actually equal to each other. That's all for today.
I think maybe the small q equals the small q momentum in the first advanced green function we have a wrong sign.
Small q
Small q in the first advanced.
in this one.
No, this is
Advanced.
Advanced one, this one. So I have small q going here along the real, along the retarded function, and
the sum should be equal to q, so yes, q should be subtracted, I guess.
so it was, yeah, it was opposite there. Well, if you find any other errors, you can also correct them as a part of the whole work.
Let's turn the speaker then. Next lecture at 2 o'clock.